Hello, in this video we're going to be talking about the evolution of the universe. How will the universe end? We've talked about the beginning, we've talked about the right now, so now we look to the future and we see how our current understanding of physics will inform what could happen to our universe. We will also talk about the role of the mysterious dark energy. So we're building off of our understanding that space and time began with a big bang where all of the matter of the universe expanded from a tiny, tiny, tiny point, and has been expanding ever since. And we look today and we see the universe expanding. So we need to try and understand if that expansion is happening, what it could mean. That means we live in a dynamic universe. It is changing. For hundreds and hundreds of years, the thought was that the universe was static, because for hundreds of years we've recorded the constellations in the same place and made the same observations of events. But it has become very clear that even though it's hard to see on our human timeline, the universe is dramatically changing. We see this when we look billions of years back in time, when we look off into distant space. So we need to understand what's going on right now to be able to predict what will happen in the future. And just like if we know all of the information there is to know about a projectile moving through the air, we can predict where it will land using the laws of physics. We can do the same thing looking at the universe. It's a little more complicated, but we know that we have a whole bunch of stuff that's expanding, and the space is expanding, and the stuff is getting further apart. So we just focus on our understanding of the most basic parts of physics first, and we talk about the four fundamental forces. Because on this scale, remember on the galactic scale, the force that dominates is the force of gravity. The gravitational force is the only force that really acts on the cosmic scale. At this scale, everything is electrically neutral, and we're certainly far outside of the range of any nuclear force. So we know that only the force of gravity is acting, and the force of gravity is an attractive force. This should then act against the expansion. This should really be slowing down the expansion because all matter is attracted to other matter. So as everything gets further apart, there's still this force trying to pull it together. Now, the expansion that began with the Big Bang, the real question is, how much stuff is there? How strong is this gravitational pull? Is it going to be strong enough to perhaps eventually win and slow everything to a halt and then pull back on itself? These are the things that we need to think about. And it depends on how much matter there is in the universe, and really it depends on the density. How much matter in how much space. So we are really interested in knowing about the density of the universe because based on our understanding of how gravitational attraction should be dominating at this level, that would tell us whether the universe will eventually perhaps reverse its expansion. For the sake of the way we're going to look at this, and honestly a lot of this is more of a historical perspective anyway, we're going to look at three different cases. One where the density is low, relatively speaking. One where it's high, and we'll look at the kind of cutoff right in between. If the density is very low, so if there's not a lot of mass, then the force of gravity will slow things down, but not enough to halt the expansion. This is a lot like something having escape speed. Even though you could throw a rock, conceivably, if you throw it fast enough, you could throw a rock that will never, ever, ever come back to Earth. That's the idea of escape speed. It will slow down, but it will slow down to some eventually fixed value and get infinitely far away and never return. So this would be what happens with low density. The mass of the universe, the attraction would slow it down, but it's expanding so quickly that it's never going to turn around. If the density of the universe was very high and there was a lot of matter and a lot of gravitational attraction, then you could imagine all of that mass would be so attracted to each other that the expansion would eventually stop. It would hit some maximum size and then the universe would collapse. We would get some kind of big crunch, and then who knows, maybe a big bang again. Seems very unlikely. And we would have a cutoff in between the two. And this is what we'll define. There is some critical density where we're exactly in the middle, where if the density of the universe was any lower, the universe would expand forever. And if the density was any higher, it would contract back on itself. There must be some number that's the cutoff in between those, and we call that the critical density. So we use rho, of course, our symbol for density, with the subscript C, critical density. All right, so here's some ways that we can chart what these possibilities look like. They largely correlate to the different shapes of the universe that we've talked about. Critical density, it turns out, would give a flat geometry. And this would cause the universe to expand. We can see here we have the scale factor, which we can think of as the size of the universe at a given point in time. If the density of the universe were equal to the critical density, then it would expand at a decreasing rate, but would eventually flatten out. If the density of the universe were less than the critical density, that would mean there was not very much mass, and we would have an open universe where, again, it's very similar. You would see the size continues to increase. The slope of this line, or the gradient, would decrease over time, but to some finite value, and it would continue off eventually, perhaps in a straight line forever. And then if the density of the universe were greater than that critical density, that's where we would eventually hit some point where the universe reaches a maximum size and then starts to collapse back on itself. And here we're back at Big Bang size. So those are the three possibilities based on the density, and they correspond to the curvature of space. Again, this goes a little bit beyond the scope of the IB, and it gets very abstract and difficult because, again, we're kind of conceptualizing curvature of a 3D space by looking at, a 2D sheet. This is a flat sheet. This is a closed curvature, and this is the open curvature. We want to remember CMB, the cosmic microwave background, and the anisotropies in it show evidence that the curvature of the universe is flat. Here again is what that looks like. We can see the CMB would look different based on the shape of the universe, and here we do have, this is the CMB that we see. It looks most like this. So flat curvature seems about right, which for a long time seemed to imply that we might be in a critical density situation. So we can use conservation of energy to derive the expression for critical density. It is similar to how we calculate escape velocity. Same kind of idea. We're talking about gravitational potential energy and kinetic energy, and trying to sort of balance these two things as one expands and it slows down because of gravitational attraction. The Cognity textbook has a nice derivation of this. I will not in this video be walking through it, but I do encourage you to take a look at it to see kind of how this conservation of energy comes into play. But the results are here and in your data booklet. And it turns out, believe it or not, the critical density depends on Hubble's constant and the gravitational constant, some other values. So 3 times the Hubble constant squared divided by 8 pi times big G, it turns out, gives the critical density of the universe. So it's a value we could pretty easily calculate. Now again, remember, Hubble's constant is something that we are constantly trying to nail down and improve. But this is what it really depends on. All right, so this equation in your data booklet is used for solving for the critical density. It is a very simple equation to basically plug in some constants to and calculate that density. The important part, though, is how we make the comparisons to that number. right, there's one other way that we can do this comparison, and it's a little bit of a simplified way to look at things. We use what's called the density parameter, and it's just a ratio. So it's a ratio of the actual density compared to the critical density. So this would be how we define it. In other words, if we had the density of the universe was less than the critical density, then this fraction would be less than 1. So our density parameter, where we're using the Greek omega, would be less than 1. A flat universe, these values would be the same, so the parameter would be 1, and in a closed universe, the parameter would be greater than 1. Again, this is kind of beyond the scope of the IB. There's a lot of equations in astrophysics that use this density parameter, and it's a lot more convenient than using values for the density. So we don't do a lot with the density parameter, but you do want to know what it is, and it refers to this comparison of the actual density to the critical density. All that being said, this was our understanding for a long time, and much like with rotation curves, we have to look at what the current understanding of physics says should be going on. It turns out none of those things are what we observe to be happening, which is very unexpected. When we look off, the main piece of evidence that we will talk about here is distant 1A supernova. We know these are standard candles. This is when a white dwarf evolves next to a binary companion and starts to siphon off some of its mass and eventually gains enough mass to overcome degeneracy pressure and go supernova. And they're really, really consistent. So we can look at distant 1A supernova, and based on our different possible models of the universe, we know how redshifted they could potentially be. And it turns out they are way more redshifted than they should be. They are much further away than we expect them to be. This tells us that the expansion rate of the universe is actually accelerating. The fact that these are so far away means the universe is expanding at a quicker and quicker rate. And so these are our three sort of conventional possibilities. What we really see, though, when we look basically at the redshift at different scale factors at different moments in the past, we see that things are way further away than they should be. That tells us we're on a curve that looks like this, that the expansion is actually getting faster and faster and faster. And there's no good explanation for that in our conventional understanding. Right? The idea is the gravitational force should be slowing everything down, but it sure doesn't look like it is. It looks like things are getting faster and faster. That's an issue because it seems to violate conservation of energy. There seems to be energy coming out of nowhere, making the universe go faster and faster and faster. So it seems that there's some kind of energy we can't account for. And so, if we can't account for it, let's call it dark energy. There seems to be a whole bunch of energy that we don't know anything about. Maybe we can't see it. Maybe we can't measure it. All right, so the main piece of evidence for dark energy that you would want to talk about and understand is how we know this is these distant supernova. There are some models that consider space itself to have some kind of latent energy. So as space expands, there's more of this energy within space to accelerate the expansion. But this is a little beyond our scope. When you do the math, though, and you look at the numbers, the dark energy in an E equals mc squared sense, when we're making a comparison, dark matter, dark energy, about 75% of the stuff in the universe would be dark energy. There's so much of this energy that we have not accounted for causing this expansion. And again, this is a case where it's really not clear that this is even energy. it's another case where we can say, well, if there was all this energy, that would cause the expansion to happen. And so uh, the dark energy was proposed in the same way that dark matter was. If there was a whole bunch more mass that we couldn't account for, uh, then that would explain why the galaxies hold themselves together and rotate in the way they do. Same idea here. If there was a whole bunch of energy that we hadn't accounted for, that could explain the expansion of the universe and its acceleration. But we really, whereas for dark matter, we have some candidates and we have measured some and seen a whole bunch of machos, for example. There is not a whole lot in terms of the dark energy candidate field. It is very wide open. The best we have is this idea that somehow space might have some energy, and this comes in with some of Einstein's relativity. But this is very, very, very mysterious and is actively being researched at the moment. This is a big difficulty in physics right now that we are up against, and it is very, very, very big area of research. So what that means for the end of the universe is a big rip as all of this stuff of the universe accelerates and expands further and further and further apart. That seems to be the way that the universe will eventually end. There is a lot to discover in the meantime. Astrophysics, again, is a constantly evolving field. There is constantly new research on dark energy, so always new and interesting things to read and learn as we continue to kind of probe into the cosmos. That's all I got for you. Have fun.